Okay, so now we'll do our next example, classic three reservoir problem. It occurs in probably every hydraulics textbook in some fashion or another. Maybe not quite laid out like this, but this is the first step towards real network modeling. In this case, what we'll have is we normally are provided with a picture of the reservoirs and their pool elevations as shown here on the figure, and then some description of the connection system, and then we're asked to find out what the flow rate is in each of the connections, and depending on how the problem is presented, we may have a demand at the junction or not, and we also may not know what the elevation of the junction is or not, but we can still solve the hydraulics even in the absence of those two information. So here's an example of a typical problem statement. Reservoirs A, B, and C are connected as shown. The water elevation in reservoirs A, B, and C are 100 meters, 80 meters, and 60 meters respectively. So in the drawing, the three reservoirs are shown with the water surface elevations indicated. We're told that there's three pipes that connect the reservoirs to a common junction, indicated by the black dot and letter J for junction. Pipe AJ is 900 meters, pipe BJ is 800 meters, and pipe CJ is 700 meters long. So the lengths are provided. In this case, we're also told the diameters of all pipes is 850 millimeters. That's a pretty good sized pipe in the whole scheme of things. We're told they're ductile iron. That's not a trivial piece of information. By knowing what the pipe's made out of, we can look up a roughness height and complete the either Darcy-Weisbach or Hazen-Williams model of the pipe behavior. We're told the water temperature is 293 Kelvin, and that's used to look up the viscosity of water. And so all the pieces one would need to solve the fluid flow in this particular case are given. And then the final part is the actual question. Find the direction and magnitude of flow in each pipe. Some of them you can do simply by looking. Okay, so the 100 reservoir number A is at elevation 100 meters. It's at greater elevation than any of the other components, and so you can almost look at it and tell that water has to leave A to go into the system. So the flow direction in that pipe is from A to the junction J. Reservoir B, we probably think water's leaving it, but we won't know until we do the solution. Reservoir C is the lowest thing, so it has to be taking water. So we know that the flow in pipe CJ has to be from the junction into C. The intermediate one, we don't really know which way it's flowing. We don't care. We're going to let the computer do it for us. First, we need to convert that particular image into a bitmap, and that's so that EPANET can import the background image and we can use it to help draw the network. And then the remainder of the problem is relatively simple extension to the previous problem. So let's switch over to EPANET. Looks like I got about 19 minutes of connection time remaining, so I think I can just do it this way. This time we'll do it from scratch, even though we actually have the example already built. So let's create a new project. Okay, so here's our new project. We'll put a title up here, 3 reservoir example. Except I did it wrong. There we go. Let me get back to the pointer thing. I don't use the text very often, so it's not surprising that I don't know how to use it. So this is the 3 reservoir example. We're going to go ahead and load in an existing base map because I happen to have one. It's example number 3. There's the base map, and let me see if I can drag the map down a little bit, and I'll drag this up. Okay, so there's the example that we'll work with. So we'll need 3 reservoirs. We'll put one of them right there for A, B, and C. So EC is 1, 2, 3. And we'll have a junction node right there. And we have the pipe. We can either draw the pipe straight, or if we want to adhere to the picture, you can draw it kind of like that. And I like to reiterate that in general, the drawing is just that. It's a drawing, and there's no huge advantage to following the layout map except possibly in dealing with a client. Let's temporarily export or unload. So there's our network. That should look very much like the original problem statement. Now we have to parameterize the different features. Reservoir A, if you recall, is not coming up because, there we go. Reservoir ID is currently 1. Let's give it the name A. And its total head was 100 meters in the problem statement. Reservoir 2 was actually B, and its total was 80 in the problem statement. And last one was reservoir C, and its total head I think was 60. We can quickly check that. 180, 60. Okay, so we've got the reservoir set. Now we need to deal with the pipes. One thing we can use is this polygon drawing tool. And what I did was draw a polygon around the whole object, and then to close it I did a right click, and now we can use the group edit feature. We're going to edit all of the pipes, and we're going to replace the diameter with 850. That's diameter in millimeters. And what that's going to do is it just replaced it for all the pipes. We can verify that by just picking a pipe, and sure enough the diameter is now 850 millimeters. 900, 800, 700. So now we'll go and manually change the lengths. So the pipes are now parameterized. The next thing we would want to do is change the project defaults. We're going to go from gallons per minute to liters per second. We'll switch the head loss to Darcy-Weisbach. And the problem's almost ready to run.
Yeah.
We have one more thing we have to provide, which is the roughness for ductile iron. And let's hope I left notes behind for doing that.
So only one friction parameter or two, like one for the flow and one for the material.
Yeah, there is a we have to tell it what the pipe material is by virtue of the roughness height, and I'm trying to see if I left. I didn't, but we're going to cheat. We do happen to know that that example is already here. Hopefully we have an input. We do. So I'm going to get the roughness height off of the input example. Maybe I will. 0.1 is what we use for roughness. And with 3 pipes, it's just as fast to do it by hand as it would be to use the group edit. Alright, so we're mostly set up for this problem. Now let's mentally review. We got the connections done. We specified pipe diameter, pipe length, node type, and node elevation. So we're pretty close to being able to solve this particular problem. What we don't know is the elevation of the junction. Currently it's set to 0. We'll leave that be for the time being. And now to run this simulation, what would we do?
Run.
Right. We would do project, run analysis, and it says the run was successful. And now we can play with the map view. Let's just have it produce a picture of the velocity. It's bigger than 100 liters per second everywhere. No surprise there. If we go to the view item, menu item, we can turn on the flow arrows and get the flow directions. We also can display the link values, and this will give us the flow rates in liters per second. So we have 3,000, so 3.07 cubic meters per second coming out of reservoir A, 0.36 cubic meters per second leaving reservoir B, and a total of 3.4 cubic meters per second coming into reservoir C. At the nodes, we could have it show the head, and we can in fact go so far as to have it display the head. And the color scheme is hard to tell, but we have 100 units ahead at reservoir A, 80 at B, 60 at C, no surprise there. And at the junction, it's showing 79 meters of head. Now watch what happens when we change to pressure. I think the units will still be the same. So we have 0 pressure in the reservoirs because we're at the free surface, and the pressure at the junction is still 79 meters, but that's because the junction's elevation is 0. So if the junction was, say, arbitrarily picking 65 meters, what would you expect that pressure term to do if we raised the junction?
Pressure would be relatively, I think, higher.
I think it'll go down, but let's find out. So it went from 79 to 14. Now, why did it do that? The total head didn't change. The total head at that node is the same 79. But because total head is elevation plus pressure, by raising the elevation, the amount left for pressure went down. So if that's the case, if the elevation of that node is 65 meters, then we expect 14, call it 15 meters of pressure. That's about 1.5 atmospheres of pressure, and that might be adequate for this situation.
No, this pressure is due to the height, or this pressure is due to the flow?
So at junction J,
Yes.
here's our junction.
Yes.
We're saying that its bottom elevation was 65 meters, which means the pipes are all connecting. And there's this one coming in like that. And so the water is above those connections. And essentially, it's telling us that that height is 14.71 meters. So this is elevation. This is pressure. The sum of those two is called the total head. Now your question was, what if the flow was 0? Let's see if I can take care of that. Close off that pipe, rerun that. Now by disconnecting this pipe, we'll see that the only thing remaining is that path, and so the pressure indeed dropped. Let's reconnect this pipe. And we'll disconnect this pipe. And now we have 12 meters of pressure. It's a consequence of the particular layout that we just specified. Let me reopen this pipe. Okay, back to mostly the original condition. Let's say that we wanted to save this particular simulation. The way to do that would be to go to our File menu, choose Save As, and we'll save it back to the example3 directory, which is what I want. And what do I want to name this? In class. And we've saved it. We also can go to the File menu and export the network, and that'll create an input file. I'm going to exit the program. Done. And let's take a look at that input file. So the input file we just made is right here. Come on, let me get the handle. Oh, it's being disobedient right now. But everything about the model is stored here in this input file. Later on, when we get to talking about the toolkit is a set of Python functions, if you will, that let us directly manipulate this file and run the program directly and directly get input and output without having to pass through the edit, run, print process that we've just been doing. So I'm going to close this file and probably stop this session because we've got 2 minutes left on the server and I don't want to lose work, and that seems like that would be a good time to stop this video and render it. So let me stop the video.